so I can post this later. Just a couple of quick announcements. This is our last day of doing virtual. I'll be back in the classroom starting on Monday. I hope everyone was able to keep up this week with the lecture videos being put online or attending class in person. You have a homework set due tonight over limits and infinity. This is the topic from last week, so the homework for that is due tonight on WebAssign. You can already be working on the definition of the derivative homework as well. That's next Friday, along with the skills quiz next Wednesday. So that's kind of where we are at this point. We've kind of developed a comfortable rhythm here week in and week out of what the class sort of is. We're moving on to a new topic today known as differentiability. Last time we looked at the definition of the derivative in terms of a limit and did a couple of examples, one long example in particular, but looked at several ways in which you can use the notion of limits to calculate derivatives. If you are trying to keep up with reading in the text, which I highly encourage you to do, then we are in section 2.7 and a little bit of 2.8 in this lecture. So what I want to start with today is acknowledging that while the derivative is always a limit, the way that we presented it last time in class isn't the only way to think of a derivative. And I want to give you a very sort of simple way of thinking about what the derivative is doing. In fact, the first couple of problems that we're going to look at together here today are all about interpreting the derivative. So looking at what the derivative says in context about a function. So I want to start with a pretty simple example here of just blowing up a balloon. So imagine that you have a balloon, you've got the little nozzle part and you're blowing into the balloon. You're blowing into it so that it will increase its volume. So we know that I'm assuming the balloon is going to be spherical, so that the volume of the balloon at any radius can be found using the common volume formula, 4/3 pi r cubed. And as I blow into the balloon, it's going to increase the radius by some small amount. And what I want to know is I want to know how quickly the volume is changing. So I want to know the rate of change, that's the derivative. I want to know the derivative of volume when the radius is 4 inches. So I've continued to blow up in the balloon. I'm going to pause at the moment the radius hits 4 inches and figure out how quickly the volume was changing at that point. So it requires a derivative to do all these things, but the way in which I'm going to do it is not the way that we did it in class last time. I'm simply going to make the following observation. Normally, the volume of a balloon is 4/3 pi r cubed. If I blow into the balloon, what happens? Well, I know that I'm going to change the radius of the balloon by a little bit. So I'm going to change the r to r plus delta r, because I've changed the radius a little bit. I also know that a change in the radius is going to equate to a change in the volume, a small change. So I'm going to add on a delta V to represent that change. So this is what the act of blowing into the balloon creates. It creates a formula where I've changed the input variable radius a little bit, and I've changed the output variable volume a little bit. And ultimately what I want to do algebraically is recover the ratio of those two things. So we want to find since slopes are rate of change, we want to find the rate of change of volume over the rate of change of the radius. That's going to give me an average rate of change. And by taking the limit of that rate of change, I can pin it down to exactly 4 inches. All right, so let's do some algebra there. So I'm going to look at the V plus delta V. The first thing I can do here is take the R plus delta R cubed term and FOIL it out or expand it out. So I don't expect you to know the formula off the top of your head from high school about expanding cubics. You cube the first term. It's 3 times the first term squared times the second term plus 3 times the first term times the second term squared. Plus the last term cubed. So if I was to take and expand this r plus delta r times r plus delta r times r plus delta r, this is what I would get. Okay, I'm then going to distribute this 4/3 pi to each piece. So we have that on the right-hand side. Okay, remember the goal is to solve for delta V over delta R. I want to acknowledge something first though. This volume that's here, I know is 4/3 pi r cubed, but I also see it on the right-hand side of the equation. So V, which represents 4/3 pi r cubed, is also on the right-hand side of the equation, which means that I can cancel those two pieces. What I'm left with then is delta V on the left-hand side. And on the right-hand side, every term has a delta R. So I'm going to factor out a delta R on the right-hand side. So if I factor out a delta R and what remains on the right-hand side, I get 4 pi r squared plus 4 pi r delta r, there's one of those left, plus 4/3 pi delta r squared. Okay, I'm almost to my goal. My goal was to find the ratio delta V divided by delta R. So if I take the delta R that's here and divide it over, I get delta V divided by delta R is what was in the parentheses there. Okay, so this tells me my average rate of change over any R value from time 0 to time R, right? Not time, radius R. So this would tell me the average rate of change from a radius of 0 up to a radius of whatever value I'm interested in. But to get the value precisely at 4 inches, I need to create an instantaneous change. And that's where we accomplish that via the limit. So I want to look at the limit of this as delta R approaches 0. And then I'm going to evaluate this. Let me put that here. Because I'm wanting the change to go down to nothing so that it's an instantaneous change. I'll have to do that on the other side as well. So you have to take the limit of both sides. And the limit on the left-hand side is just the derivative at R, right? The limit as delta R approaches 0 of delta V over delta R. From last class, we said that that is the definition of the derivative. So that is the derivative of volume at a particular radius. But on the right-hand side, if I take the limit as delta R goes to 0, here's delta R, it goes to 0. Here's delta R, it goes to 0. What's left on the right-hand side is just this term right here. It's the only term that didn't have a delta R. You get 4 pi r squared on the right-hand side. So I know that the derivative for this problem is 4 pi r squared. So this is a different way of calculating the derivative than we did last class, but it's meant to be a way to show you what the derivative actually is. We wouldn't want to calculate derivatives in this way. We're going to have much better ways to calculate them going forward. But it tells you what you're doing every time you do calculate a derivative. You're making a small change in one variable that creates a small change in the other variable. You're then looking at the ratio of those changes. You're solving for the ratio of those changes. And you're taking the limit as, in this case, delta R goes to 0. That, in essence, is what the derivative is. And so for this problem, we obtain the derivative formula, and we're trying to look precisely when the radius is 4 inches. So if the radius is 4 inches, what's the derivative of volume? Well, it's 4 pi 4 squared, or 64 pi. Let me give you a decimal approximation of that. That is 201.0618. And here's a question I really want to ask, and that is, what are the units of this answer? Does anybody have a guess what the units are for this answer? The units for radius are inches here. The units for a derivative are the same as the units of the ratio that formed the derivative. So the ratio that formed the derivative is volume divided by radius. So Juan, you're almost there. Okay, Melanie is saying inches squared. Okay, let's talk about this. So I said it's the same as the units for the ratio, right? So the units for volume are inches cubed, right? The units for radius are inches. So the units for the derivative are inches cubed divided by inches. And Melanie is saying that it's inches squared. Okay. I do agree that it reduces to inches squared. I want to caution you in doing that, though, because you may miss the meaning. And what we're after today is meaning. So I actually want you to think of this as inches cubed per inch. And what this number is actually telling me is how many inches cubed of volume I can expect to increase by if I increase the radius by 1 inch. So kind of write this right here. This number represents the amount of increase, and it's increased because that number is positive. The amount of increase in volume, which is measured in inches cubed, per inch increase in radius when the radius is 4 inches. Said another way, whatever the volume is at 4 inches radius, we expect the volume at 5 inches of radius to be 201.06 inches cubed larger. Does that make sense? That's the most important part of this example, is the units, talking about what they mean. Does it make sense that this is saying that if you were to add another inch to the radius, going from 4 inches to now 5 inches, you would expect to increase the volume by about 201 inches cubed? Are there any questions about that? Okay. The other thing I wanted to point out is that Melanie is not wrong. Inches squared makes a ton of sense here. Not only does it reduce to inches squared, but the formula that we came up with for volume, this 4 pi r squared, that turns out to actually be the formula for the surface area of a sphere. So it makes a ton of sense that this would be in inches squared, because what you're doing when you're calculating the derivative of volume is you're calculating a change in the surface area. So this is actually surface area change that we're experiencing here. I mean, we're changing the volume, but that's also expanding the surface area of the sphere. So it makes sense that this would be inches squared here. The two concepts are related, right? The derivative of volume would be area, right? The derivative of area would be length, right? These are the kinds of things that we're going to try to connect this semester. All right, so let's see if we can do some more examples to make sure we understand what the units are with derivatives, like what the context is here when we're calculating them. So here I have an example that's related to what we call drug sensitivity, which is the temperature change that occurs in a person based on dosing them with a drug. So the units here for temperature, T, are in Fahrenheit, degrees Fahrenheit, and the dosage is in milliliters. So degree temperature of a patient in terms of the dosage that is administered. So what is meant by T of 50 equal to 0.75? Well, T of 50 equal to 0.75 means what? Remember, it's temperature change. It means that a 50 milliliter dose increases patient temp by 0.75 degrees Fahrenheit. Okay, that's what this is telling me. And a person's sensitivity to the drug is how quickly that change occurs. So the rate of change of that temperature change. So the sensitivity here function is simply the derivative of this function that we looked at before. So my question is, what are the units of sensitivity here? So S of Q equal to T prime of Q. What are the units? See, this is where the Leibniz notation is more interesting. Remember that T prime of Q, another way to write that is the derivative of T with respect to Q. The reason that this is the Leibniz notation for the derivative is more informative is it gives you an idea of what the ratio is. So remember that the units of the derivative are the units of the ratio being calculated. So what would the units be if this is the ratio? Feel free to answer, anybody. Can answer over mic or you can type it into chat. Yes, it would be degrees Fahrenheit per milliliter. So that's what the derivative here is measuring, is the rate at which temperature increases per additional milliliter of dosage introduced. So finally, if I said, what then is S at 50? That's the derivative of temperature at a dosage of 50. Even though in this part A, a 50 milliliter dose would increase the patient's temperature by 0.75, continuing to dose that patient according to this actually would drop the temperature. So this is saying, using the units here for the derivative, this is saying that at a 50 milliliter dosage, an additional milliliter would drop the patient temperature by approximately 0.02 degrees Fahrenheit. Remember, it's always about the next thing, right? Like on the balloon, the number told us what we would expect going from 4 inches to 5 inches, right? One additional unit. Here, it's telling us what we'd expect going from 50 milliliters to 51 milliliters. One additional unit of dosage, we would expect it to drop by around 0.02 degrees Fahrenheit. That's what this tells me. Are there any questions on that page? It's guaranteed on your exam you're going to have some stuff like this to deal with. It's a really important concept out of the first third of the course. All right, we're going to keep doing this. So let's look at one more example, kind of like this. So this one, we're going to analyze manufacturing costs. So suppose that we have a company that manufactures rope, and the costs associated with manufacturing rope depends on how many feet of rope are produced. So we've got cost as a function of feet in this case. So when we say, what does it mean to say C of 2000 equal 800? 2000 is referring to feet of rope. 800 is referring to total cost. In other words, it costs a total of $800 to produce 2,000 feet of rope. That's just the function. All right. So the units of the derivative. I want y'all to tell me here, what are the units of the derivative? Multiple ones of you. I want to see you type it in chat. What are the units here? Remember what I did on the last one, right? I took the derivative notation, I transformed it to the Leibniz notation, and then I looked at the ratio of the units involved there. So do the same thing here. Okay, we've got one person that says feet per dollar. We've got another that says dollar per feet. Do we have anybody else want to chime in? Okay, so this is the fact that we've got two different answers here is good, because it leads me back to the way to do this. That's sort of foolproof. If you have C prime of X, right, that's the Newton notation. C prime of X is the same thing as the derivative of C with respect to X, right? So the function variable goes on top, the input variable goes on bottom, and now you're just replicating the units. The units for C are cost, the units for X are feet. So the units here are dollars per foot. Right? So the derivative in this problem would tell me how many additional dollars does it cost to manufacture one additional foot at a particular production level. Okay, so now everybody gets to answer. There's a learning catalytics question associated with this. Let's see if you've been paying attention here. So the question is specifically about C prime of 5,000 equals 0.1 in this context. So if I told you that C prime of 5,000 was equal to 0.1, which of these A through D correctly describes what that means? I'll give you all a little bit of time to get logged in here. Session ID is at the top, and give me an answer. All right, almost all of you have responded, and we're a little bit torn. The correct answer is B. Let me go through each of these one at a time just to make sure we understand why they were wrong. It says it costs 10 cents per foot of rope to produce 5,000 feet of rope, resulting in a $50 cost for 5,000 feet. So 10 cents per foot times 5,000 is $50. The reason this is not correct, and this is the reason that factories exist in the first place, is the cost per foot is constantly changing, right? When they first started creating the rope, it's very expensive, right? But in a factory setting, the more machinery you have, the more capability you have to mass produce something, the cheaper per foot of rope it would be to produce in those situations. So this 10% per foot is not true for all of the 5,000 feet that came before. It's true only at this particular point in time, the point in time where we have produced 5,000 feet. At that moment of production, the cost is 10 cents per additional foot, which is why B is correct, right? So at the moment in time you've produced 5,000 feet, the cost to produce one additional foot will be 10 cents, right? So going from 5,000 feet to 5,001 feet, you would expect a 10% cost increase. That's what this says. The cost per 5,000 feet of rope is 10 cents. No, even though the units are correct there, because it's cost per feet, the context there is not correct, okay? The same thing is true on D. The context here is not correct because I'm not talking about anything about the first 5,000 feet, okay? So remember, the derivative is a local thing. It only talks about what happens over the next one unit starting from where you are. It doesn't talk about any of the stuff that happened before. So if your explanation here involves anything about the 5,000 feet before, it'll be wrong. Okay, so B is the only one that makes sense here. So going back to this, the official answer here, I would say, is that C prime of 5,000 equals 0.1, means that for each additional foot of rope produced, beyond 5,000 feet, we expect a cost increase of 10 cents. All right. On D, suppose that C of 2000 is 800 and C prime of 2000 is 0.35, estimate 2001. Well, it's literally what the definition of the derivative is telling us here, that if you start at 2000 and over here on the side, you know, at 2000 is $800, right? This is the total cost as a function of the rope produced. You're starting here, and you know your derivative is 0.35. Derivative is slope, right? So your slope is 0.35. Well, this is always a distance of 1. So that means this must be a distance of 0.35 if the slope is going to be 0.35, right? So the slope, which is the derivative, is 0.35 here, which means what's this new value? Well, this new value at 2001, since it's always 1 away, is $800.35. So we would estimate that C 2001 is $800.35. Slightly more for one. At that point, you're growing at a rate of 35 cents per additional foot. Up here, you were growing at a rate of 10 cents per additional foot. So the the rate of cost increase has gone down. It's becoming cheaper to produce extra feet of rope, the more feet of rope that you've produced. So that brings me to the final question here. Do you think that C prime of 2000 is less than, equal to, or greater than C prime of 8000? Based off the logic that we've developed here, we would say that C prime of 2000 is greater than C prime of 8000. We're generally seeing that cost inflation decreases as production increases. It becomes cheaper to manufacture the higher your production is. Now, there's a limit to that, right? So there's a limit based on the size of the warehouse, the number of employees, number of materials available. There's always a limit to these things. It won't always be the case that increasing production decreases cost increases, but that's what we would expect. Right. This is not the last time we're going to talk about these things this semester. It's you know, here in about 4 weeks, the rest of the semester is about this kind of stuff, right? We're going to be looking at word problems involving these kinds of rates of change and trying to decipher them based on the tools of calculus. All right, what I would like to do now is talk about, you know, we know that the derivative is a limit, and we've calculated limits in this course. We also know that sometimes limits fail to exist. So in the case of the derivative, are there times when the derivative fails to exist? And the answer is yes. And I want to illustrate it with the sort of canonical example here. It's the example that you would see in every course as a first example of a place where the derivative doesn't exist. And that's the absolute value function. So if you recall, the absolute value function looks like this. Remember, derivatives are all about slopes, right? So here you have the slope of this function is 1 on the right-hand side. To the right of 0, the slope is 1. And to the left-hand side of 0, the slope is -1. So that sort of begs the question, what is the slope at x equal to 0? So in other words, if our function was f of x equals square root of x, what we're trying to do here is determine what is the derivative of that function at 0? What is the slope at 0 on this graph? Well, the only thing I can do is use my limit definition. Looking at the picture, I don't have a good idea of what it's going to be, but I do know from class last time that we can calculate derivatives using a limit. And the limit we need is the limit as h goes to 0 of, so remember it's this, it's f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. That's our derivative limit formula from last class. So here I'm looking for f prime at 0, right? I want to know what's happening at 0. So f prime at 0 would be the limit as h goes to 0 of f of 0 plus h minus f at 0 over h. So let's see if we can take each piece here and figure out what that is. F of 0 plus h, well, the function is the absolute value function. So if I replace x with 0 plus h, this will be the absolute value of 0 plus h minus the absolute value of 0 divided by h. But this is, it reduces to the absolute value of 0 is just 0, 0 plus h is just h. So this reduces to the absolute value of h divided by h. And if you recall, we actually looked at a limit very similar to this when we were doing limit problems. Remember, with absolute values, you have to calculate two limits. You have to calculate the limit, and in this case is h approaches 0 from the right, and you have to calculate the limit as h approaches 0 from the left. So if I look at this and I'm to the right, if I look at this and I'm to the right of 0, right, then h is approaching to the right of 0. Those are positive values. So this would be h over h, which is 1. If I'm approaching to the left, then the values of h in the top are negative. So I need a negative h for the absolute value there. And you get negative h divided by h is negative 1. It basically tells me what the picture tells me, right? If you're approaching 0 from the right, your slope is 1. If you're approaching 0 from the left, your slope is negative 1. Now, because this is a limit problem, what can you say about the two-sided limit? Since the limit from the left didn't equal the limit from the right, according to our definitions that we've used in this class, because those are not equal, the limit and hence the derivative do not exist at x equal to 0. So this is our first example of a function where I cannot take the derivative at a specific point. If I try to take the derivative at 0, it will fail. And there's a really good reason why, right? The really good reason why is derivatives are slopes of tangent lines, right? So it's not that there's not a tangent line here, it's that there's too many. So there's a tangent line, right? But there's also a tangent line. Both those lines would be tangent at the corner there. So it's not that we don't have a tangent slope, we just have an infinite number of them actually. And so I can't settle in on one single value because, you know, the values coming in from the sides don't agree. So what actually happens at the point is a bit of a mystery. You can't calculate the derivative there. So this is what we call a corner point. And at all corner points, derivatives are undefined. You cannot take the derivative at a corner. All right, so a question that immediately sort of follows here, and a definition that follows, is the definition of differentiable. So a function is differentiable at a point if the derivative at that point exists. On the previous example, right, on the previous example, we would say that the absolute value function is not differentiable. I cannot take the derivative, not differentiable at 0. But it is differentiable everywhere else, right? At 1, it has slope 1, so the derivative's 1. At -5, it has slope -1, so the derivative's -1. I can take the slope and hence the derivative anywhere on this graph except at 0. So this function is differentiable, is not differentiable at 0, but it's differentiable at every point other than 0. So differentiability is a local concept. It's a pointwise concept. And just like continuity was a pointwise concept, we still had a definition for continuity on an interval, right? So if you say that something's differentiable on an interval, it means it's differentiable at every point in the interval. We don't talk about differentiability at endpoints because at endpoints, you don't have a limit from the left and a limit from the right. So we don't discuss differentiability of endpoints. It's always an open interval. Every point in the interval needs to be differentiable for the interval to be a differentiable interval. The question that should immediately pop into your mind is the previous example here is continuous, right? This is a continuous graph. There are no holes in this graph. There's no place where I have to lift my pencil on this graph. But yet there was a point where I couldn't take the derivative. So is the reverse true? Are there some differentiable graphs where I can take the derivative, but those graphs are not continuous. So that's the question I have for you is, are there functions that are not continuous at a point, but still differentiable there? And so I want you to answer this question. What do you think is true? Is it possible to be able to take a derivative even at a place where things aren't continuous? So the learning catalytics question for this should be out there for you. Let's see what your response is. All right, most of you have answered, and a little surprised by this. 71% of you said, yeah, I can take the derivative at a place that's not continuous. Think about what it means to not be continuous. If you're discontinuous at a point, you have like a jump or an asymptote or all these things we talked about earlier in the course, there's some break in the function. Most of the time, that's because the limits don't exist at those points. A derivative involves taking limits at a point. So if the limit didn't exist at a point, the derivative wouldn't exist there either. In fact, it's always the case. I don't say always very often in this course, but it is always the case that if you are not continuous, you are not differentiable. And I want to talk about that a little bit. There's a theorem here that says if f has a derivative at a, then f is automatically continuous there. Let me talk about that for just a second. If f of x is differentiable at x equal to a, that automatically implies f of x is continuous at x equal to a. In mathematics, we do a lot of these what are called if-then statements. They're called conditional statements. If something is satisfied, then something else is true. We have what's called the converse of those statements, right? The converse of those statements is reversing it, and the converse is not true, right? So here's just a normal example. If it's raining, then it's cloudy, right? Raining implies cloudy, but the reverse or the converse of that's not necessarily true, right? The converse is if it's cloudy, then it's raining. Well, that's not necessarily true. It's the same with things like that in mathematics. If I say if f of x is differentiable, that implies that f of x is continuous. The converse of that's not necessarily true, right? So the converse is not necessarily true. The converse is f of x continuous implies f of x differentiable. We know that that's not the case. The example we just gave was the absolute value function at x equal to 0. The absolute value function at x equal to 0 is the example of a continuous function that's not differentiable. So just because you're continuous doesn't mean you're automatically differentiable. But if you're differentiable, you're automatically continuous. Okay? Now, a better way to think of this statement mathematically is what we call the contrapositive. The contrapositive is always true. What is the contrapositive statement? Okay, a contrapositive is you reverse it and you negate it. Okay, so take this statement, this if then statement, reverse it and negate it. What does it say? If I reverse the statement and I negate it, meaning take the opposite of what it says, right? The opposite of is continuous is not continuous. So reverse it, negate it. What does it say? So in the example of the, if it's raining, then it's cloudy, reversing that would be, if it's not cloudy, then it's not raining, right? If it's not cloudy, then it's not raining. That's also true. Here, it would be if f of x is not continuous, then that automatically implies that f of x is not, yeah, y'all are getting it, differentiable. So that is another way to think of this result. Differentiability automatically gives you continuity. Failing continuity forces you to fail differentiability. These two things are mathematically linked. But continuity doesn't automatically guarantee differentiability. So what we say is the following, is that continuity is a necessary but not sufficient condition for differentiability. Meaning continuity, you must be continuous to be differentiable, but just because you're continuous doesn't mean you're differentiable. Okay, continuity is a necessary but not sufficient condition for differentiability. All right, that's as far as we can go today. We will pick this up next time. I'm actually going to prove that this is true to you next time. It's kind of an important proof for us to look at together, so I didn't want to just put it in the notes and not say anything about it. So we'll actually prove this next time, and then we'll make a list of ways in which derivatives can go bad, okay? So we'll finish this off at the beginning of class on Monday and then talk about graphing derivatives. That'll be our topic for Monday. All right, y'all have a great weekend.
Thank you, you too.